Hello students, hope you all are fine. Today we will discuss an interesting topic from electronics, that is the transistor. What is a transistor? Transistor is a three-terminal semiconductor device whose two sides are extrinsic semiconductor of the same type and the middle portion is of the other type extrinsic semiconductor, like PNP transistor or NPN transistor. In a PNP transistor, N-type semiconductor is joined to two P-type semiconductors, and in NPN transistor, a P-type semiconductor is joined to two N-type semiconductors. So, in a transistor, there are three main parts or three main terminals called the emitter E and the collector C and the base B. The emitter is represented by E, the base is represented by B and collector is represented by C, as you see in figure. This emitter portion or E portion is heavily doped. The base B is comparatively lightly doped and the doping level of the collector or C is in between this emitter and base doping levels. The collector is quite wide. That means the width of the collector is more than the base or the emitter. The base portion is thin. The collector is made wide because it must dissipate more heat than emitter or the base junctions. So you can see that a transistor may be regarded as two junction diodes joined back to back, like one in emitter and base junction and another one in the collector and base junction. So there must be two depletion layers in these two diodes, but the two depletion layers must be of different width because the doping levels are not equal in emitter, base and collector regions. Because you know already that emitter is heavily doped, so there must be majority charge carriers in great numbers. So in the emitter base junction diode, the depletion layer must be thin, and in the collector base junction the depletion layer width must be a little bit wide. Now let me discuss how does a transistor work. Here I am taking NPN transistor as example. The emitter portion of the NPN transistor is joined to the battery negative terminal of the battery VEB, and the positive terminal of this battery VEB is joined to the base, and the collector portion is joined to the positive terminal of the battery VCB, and the negative portion or the negative terminal of the battery VCB is joined to the base. So base is common here, and you should always remember that the emitter base junction should be always forward biased and the collector base junction should be reverse biased. The heavily doped emitter emits a great number of free electrons into the base, and this base region is lightly doped, so it contains less number of charge carriers, that is holes. So there will be recombination of holes with electrons, but the electrons will be more in number because the emitter is heavily doped than the base. So at least there will be recombination of at least 5% electrons, and the remaining 95% electrons will flow to the collector region, and there is a positive voltage applied by the battery VCB in the collector region. So this positive voltage will attract the electrons to flow through the circuit. As soon as the electron from the emitter combines with a hole in a base region. In the base region, an electron leaves the negative terminal of the battery VEB, and at the same time the positive terminal of the battery VEB receives an electron from the base. So there will be generation of the base current, which is mentioned as IB. Similarly, each electron that flows from the collector to the positive terminal of the battery VCB, an electron will enter from the emitter to the negative terminal of the battery VEB. So there is a collector current, an emitter current, and the base current. So the emitter current must be the sum total of the base current and the collector current. So we can write that IE is equals to IB plus IC. And IB is here very less than IC, because IB is mentioned as base current and IC is the collector current. So IC or the collector current will be higher than the base current. This is transistor action. There are two current gains in a transistor. One is called alpha and another one is called beta. Alpha is defined as the ratio of the small change in the collector current to the small change in the emitter current when collector base voltage is kept constant. That is, alpha can be written as alpha is equals to delta IC divided by delta IE at constant VCB. Similarly, beta is defined as the ratio of the small change in the collector current to the small change in the base current. That is, beta is equals to delta IC divided by delta IB at constant VC. There is a relation between alpha and beta. We can derive it from the equation IE is equals to IB plus IC. So, alpha must be equals to beta divided by 1 plus beta, or we can say that beta is equals to alpha divided by 1 minus alpha. The value of alpha is between 0.95 to 0.99 and beta's value is from 20 to 100. So we can see that the value of alpha is less than the value of beta. There are three configurations of a transistor, commonly common base circuit or CB circuit, common emitter or CE circuit, and common collector or CC circuit. You can see in the figures the circuits are given there. The common emitter or the CE circuit, here you can see that the emitter is grounded, and in the common base configuration you can see the base is grounded, and in the common collector configuration you can see the collector portion is grounded. So they are named accordingly. Often the common lead is connected to the ground and it is used as the reference point for the entire circuit. The common emitter characteristics are the different graphs drawn between different voltages and currents for a transistor. When the emitter is taken as the common terminal, that means the emitter is grounded or at zero potential. Base is the input terminal and collector is the output terminal. The CE mode, that is the study for the common emitter characteristics of an NPN transistor, is shown in the figure. The input or the base characteristic curve is drawn between VBE and IB at constant VCE. Current IB is 0 until VBE crosses the barrier potential, that is 0.7 volt for silicon and 0.3 volt for germanium. The curve is similar to that of the PN junction diode. IB, after the barrier potential, IB starts increasing at a slower rate then rapidly. The input resistance Ri of the transistor can be calculated from the input characteristic curve. Ri is defined as delta VE divided by delta IB at constant VCE. As we can see, the input characteristic is a non-linear curve, so Ri will vary. At any point of the curve, Ri is equal to the slope of the tangent to the curve. The output characteristics is the graph drawn between collector emitter voltage VCE and collector current IC at constant IB or the constant base current IB. This is called the output characteristic curve of the transistor. As we can see from the graph, when the voltage VCE increases from 0 to about 0.5 or nearly 1 volt, the collector current IC increases rapidly. This value of VCE is called the knee voltage. Once the voltage VCE exceeds the voltage VBE, so that the collector base junction is reverse biased, the output current IC varies very slowly but linearly with VCE for constant IB. Beyond this knee voltage, the output resistance of the transistor is quite high. If we increase VCE more, nearly about 40 volt, the collector diode then breaks down. The current increases almost vertically as it happens in diode. This value of VCE is called the collector emitter breakdown voltage, but a transistor should not be operated in this voltage. From the output characteristic curve, we can find out the value of beta, which is equals to delta IC divided by delta IB. And we can see this varies from 20 to 100. But in a transfer characteristic curve, we plot IC against IB. That means we vary base current IB and see the changes in collector current IC, and thus we get the transfer characteristic curve when VCE is kept constant. From this curve, we can see that it is a straight line, and we can again calculate current gain beta is equals to delta IC divided by delta IB from this curve. And from we can see that throughout the curve the slope is same, so beta will be same for constant VCE. We can find three regions from the output characteristic curves. They are the saturation region, the active region, and the cutoff region. Transistors can be operated in different regions according to our needs. As we can see, the shaded region towards the left of the saturation line, that is OA, is called the saturation region, and in this part VCE is less than VBE. So both the junctions are forward biased, and IC here is not dependent on the value of current, input current, that is IB. The shaded region lying below IB is equals to 0 is called the cutoff region. Here IC is nearly equals to 0. That means in this region the transistor works as a switch. It turns over rapidly from off state to on state when IC becomes non-zero value from the zero value. And the non-shaded central region of the output characteristic curve is called the active region. In this region, emitter base junction is forward biased, but the collector base junction is reverse biased in this region. So the transistor can work as an amplifier in this active region. So when we have to get amplification, we should operate the transistor in this active region. Transistor has a very unique property, that is the amplifying action. The emitter base junction is forward biased and the base or collector junction is reverse biased in a transistor. So the resistance of the emitter base junction is much less than the resistance of the collector base junction. That means we can say that R PEB is very less than RBC. So power dissipated in this emitter base junction should be mentioned as PEB is equals to IE square into REB. Similarly, the power dissipated in the collector base junction mentioned as PBC is equals to IC square into RBC. As we know that IB is very smaller than IC, so we can write that IC is nearly equals to IE. That means the collector current is nearly equals to the emitter current. So REB must be very less than RBC, and we have already PBC will be greater than very greater than PEB. That means the power dissipated in the collector base region will be higher than the power dissipated in the emitter base junction. So this can be looked up as the amplifier action. So the output is amplified.